$12 of copper pipe heated a cabin for 3 winters. No pump, no electricity, no moving parts. Here's why the heating industry buried it. First off, your furnace uses a pump to push hot water through your house. That pump runs on electricity, breaks down every few years, and costs hundreds to replace. But there's a version of this system that doesn't need a pump at all, because the water moves itself. It's called a thermosiphon, and the physics behind it is so simple that it makes every forced circulation heating system on the market look like an over-engineered scam. When you heat water, it gets lighter. The molecules spread apart, the density drops, and the hot water rises. When it cools down, it gets heavier and sinks. If you connect a heat source at the bottom to a radiator at the top with a loop of pipe, the hot water rises through one side, dumps its heat into the room through the radiator, cools down, and falls back through the other side to get reheated. No pump, no controller, no thermostat. The temperature difference between the hot side and the cold side is the engine. As long as there's heat going in at the bottom and a place for it to come out at the top, the water circulates on its own forever. This isn't theory. This is how every home in America was heated before electric pumps existed. The math behind it is surprisingly precise. The driving force of a thermosiphon is the difference in water density between the hot leg and the cold leg multiplied by the height of the loop and the gravitational constant. Water at 180 degrees Fahrenheit weighs about 60.6 lb per cubic foot. Water at 100 degrees weighs about 61.7. That 1.1 lb difference per cubic foot, spread across a 5 ft tall loop, creates enough pressure to push water through 3.4-in copper pipe at a steady flow rate, without any mechanical assistance. The taller the loop, the stronger the push. The wider the pipe, the less friction resists it. A researcher at the MDPI published a direct comparison showing forced circulation systems are 63% more thermally efficient than thermosiphon. But that efficiency gap exists because pumps can push water through narrow pipes at high speed. When you use wide pipes in a tall loop, the thermosiphon closes that gap dramatically. And it does it with zero electricity, zero maintenance, and zero parts to replace. Before we get into how to build one for almost nothing, here's why this disappeared from the conversation. Second, the history. In 1831, an engineer named Angier March Perkins filed British patent 6146 for the first high-pressure hot water central heating system. It was a coiled copper pipe loop that circulated water through a building using nothing but convection. No pump, no fan, no bellows. His father, Jacob Perkins, had already patented a 2-phase heat tube in 1836 that could transfer heat across a room using a sealed copper pipe with no moving fluid at all. By the 1880s, mass-produced cast-iron radiators connected to gravity-fed hot water loops were standard in homes across Europe and the United States. The water rose when heated, fell when cooled, and the system ran itself. For 50 years, this was just how heating worked. Then, electric circulation pumps arrived, and the heating industry discovered something that changed everything. A pump-driven system doesn't need the careful slope, the wide pipes, or the elevated tank that a thermosiphon requires. You can run smaller pipes through tighter spaces, install the boiler anywhere in the house, and charge the homeowner for the pump, the controller, the expansion tank, and the annual service call. The thermosiphon had no recurring revenue. The pump system had plenty. By the 1950s, forced circulation had replaced gravity systems in nearly every new build. The thermosiphon wasn't banned. It was just no longer taught, no longer sold, and no longer installed by licensed contractors who made their money on parts and service. Today, the Maryland Green Construction Code explicitly prohibits thermosiphon circulation loops in certain applications. Not because they don't work, but because the code was written around pump-driven systems, and there's no compliance pathway for a loop that runs on physics alone. The International Residential Code requires all hydronic heating systems to include listed and labeled components, which means a brand name, a model number, and a UL sticker. A loop of copper pipe soldered together in a garage doesn't have any of those things. The physics works perfectly. The paperwork doesn't exist, and the people who write the paperwork have no financial reason to create it. The parallels to the sand battery story are exact. A heating method that uses common materials, requires no maintenance, generates no recurring revenue, and can't be monopolized faces systematically higher barriers than one that requires proprietary equipment and annual service. The Thermosiphon isn't suppressed by a conspiracy. It's suppressed by an economic system that can't profit from it. But the physics never stopped working, and the material that makes it work best has been sitting in hardware stores for 200 years. Third, the material. Copper's thermal conductivity is 401 W per m Kelvin. That's 70% higher than aluminum and 8 times higher than steel. When hot water flows through a copper pipe, the heat transfers through the pipe wall and into the surrounding air faster than through any other common metal. That's why copper was chosen for radiators, for heat exchangers, for brewing equipment, for anything where you need heat to move from one place to another as fast as possible. But here's the part that makes copper almost unfair for a thermosiphon. Copper heat pipes, which are sealed tubes with a small amount of fluid inside, achieve an effective thermal conductivity of 10,000 to 100,000 Dwd per m Kelvin. That's 250 to 500 times the conductivity of solid copper. The fluid inside evaporates at the hot end, travels as vapor to the cold end, condenses, and wicks back down. No pump, no electricity. Just phase-change physics moving heat at a rate that makes every other material look like an insulator. You don't even need a heat pipe to make this work. A simple open loop of 3.4-in copper pipe filled with water, connected to a heat source at the bottom and a radiator panel at the top, will circulate on its own with as little as 3 ft of height difference between the inlet and the outlet. The wider the pipe, the less friction. The taller the loop, the stronger the convective force. A 1-in copper pipe with a 5 ft rise produces enough natural circulation to deliver 6,800 to 13,600 BTUs per hour from a wood stove coil. That's enough to heat a sealed bedroom in the dead of winter without turning on a single switch. Now, here's what the actual bill looks like. The real cost depends on how much pipe you need. A basic thermosiphon loop for a single room requires about 20 tatpradov of 3 to 4-in copper pipe, a handful of elbow fittings, some solder, and a small flat panel radiator or a coil of finned copper tube mounted on a wall. The copper pipe itself runs about 60 cents per foot at a hardware store. 20 ft costs $12. The fittings add another 10 to 15. The radiator panel can be salvaged from any old baseboard heater, or built from scratch with copper tubing and aluminum fins for under $30. Total build cost for a working single-room Thermosiphon heating system under $75. Compare that to a forced circulation hydronic system at $3,000 installed. Here's what you need to know before you build. The loop must slope continuously upward from the heat source to the radiator. Any dip in the pipe creates an air pocket that blocks circulation and kills the system. Every horizontal run should have a slight upward angle, even if it's just a 1/4 per foot. The pipe connections should be soldered, not compression fitted, because compression fittings create turbulence that slows the weak convective flow, and the system must be filled completely with water before you fire it up with an expansion tank or an open vent at the highest point to let air escape and absorb thermal expansion. The critical dimension is pipe diameter. 3 to 4-in is the minimum for a thermosiphon to overcome friction losses. 1-in is better. Below 3 to 4 in, the friction in the pipe walls exceeds the convective driving force and the water stalls. This is the single most common reason DIY thermosiphon builds fail. People use 1 to 2 in pipe because it's cheaper, and the system never circulates. A homesteader on the of a small cast-iron stove connected it to a loop that rose through the wall into a radiator panel in the next room, and let gravity do the rest. The system heated his workshop to 68 qualif Fahrenheit on nights when the outside temperature dropped below zero. He spent less than $100 on materials and hasn't touched the system in 4 years. The only maintenance is filling the loop with water once a season to replace what slowly evaporates through microscopic leaks at the solder joints. For a larger home, scale the loop. Run the copper through multiple rooms in series, with each radiator panel mounted slightly lower than the one before it, so the water flows downhill after releasing its heat and returns to the stove at the lowest point. Add a small expansion tank at the top of the loop to absorb pressure changes as the water heats and cools. The entire system can heat a 1-200 circulates home if the stove produces enough BTUs and the pipe diameter is at least 1 in. There's another option that most people don't consider. Instead of running the thermosiphon from a stove, you can run it from a solar thermal collector. A flat plate collector is just a black painted copper coil inside an insulated box with a glass cover. The sun heats the copper. The water inside rises through the pipe to a storage tank mounted above it, and cool water falls back down to get reheated. The entire system runs on sunlight with zero electricity. Mother Earth News published detailed plans for an inexpensive thermosiphon solar collector in the 1980s that could heat domestic hot water for a family of 4 using materials from a hardware store. The design hasn't changed because the physics hasn't changed. Hot water rises. Cool water falls. Copper moves the heat. If you don't have a wood stove, you can use any heat source. A propane burner, a rocket mass heater, even a solar thermal collector on the roof. The thermosiphon doesn't care where the heat comes from. It only cares that heat goes in at the bottom and comes out at the top. Solar thermosiphon systems are standard in Israel, Greece, Turkey, and Australia, where rooftop solar collectors feed hot water tanks mounted above them with zero electricity. Over 60 million solar thermosiphon water heaters are installed worldwide. The technology isn't experimental. It's the default in most of the world. The only country where it disappeared from residential construction is the one where the heating industry had the most to lose. And then there's one more thing copper does that no other pipe material can match. Copper is naturally antimicrobial. Bacteria, algae, and biofilm that clog steel and plastic pipes don't survive on copper surfaces. A study published in the journal Applied and Environmental Microbiology found that copper eliminates over 99.9% of bacteria within 2 hours of contact. That means a copper thermosiphon loop stays clean internally without chemical treatment, without flushing, without filters. Steel pipes corrode internally and build up rust scale that narrows the pipe diameter and kills flow rate over time. Plastic pipes, PEX especially, leach chemicals into the water at high temperatures and can't handle the sustained heat that a thermosiphon near a wood stove produces. Copper handles temperatures up to 400 degrees Fahrenheit without degradation, stays clean biologically, and maintains its internal diameter for the life of the building. There's a reason plumbing in Roman aqueducts was made of copper and lead, and there's a reason the copper survived while the lead didn't. The savings compound fast. A typical forced air gas furnace costs $900 per year in fuel and electricity. A wood stove thermosiphon running on scavenged or self-harvested firewood costs effectively nothing after the initial build. Even if you buy cordwood at $200 per cord, A thermosiphon stove system burns 30 to 50% less wood than a conventional stove because the heat goes into water and radiates from copper instead of rising straight up the chimney. Over 10 years, the difference between a thermosiphon and a gas furnace is $10,000 to $15,000 for a $75 build. The reason you've never seen this in a hardware store isn't that it doesn't work. It's that there's nothing to sell you twice. A copper loop with no pump, no controller, no filter, and no moving parts generates zero recurring revenue for the installer. The HVAC industry standardized on forced circulation because pumps break, controllers fail, and service calls pay. A thermosiphon just sits there, moving heat year after year, asking for nothing. Think about that for a second. The Roman hypocaust moved heat through stone channels 2,000 years ago. The Korean ondol stored heat in stone slabs 5,000 years ago. The Thermosiphon moved heat through copper pipes 200 years ago. Every civilization that needed warmth figured out how to move and store heat using common materials and basic physics. The only civilization that forgot is the one that turned heating into a subscription service. Angier March Perkins proved this worked in 1831. Every radiator in every Victorian home ran on it. 60 million solar units worldwide still run on it today. The physics hasn't changed in 200 years. The only thing that changed is who profits from your heating bill. If a $12 copper loop can heat your home with no electricity and no moving parts, wait until you see what a $300 drum of sand does to your heating bill all winter. Same thermodynamics, completely different storage method. That video is right here. If this story changed how you look at the simple pipes in your walls, please subscribe and like the channel. We are uncovering the history and technology they tried to bury. Let's build a more efficient future together. The next hidden treasure of engineering will be revealed soon.